Everybody has their quiz. Let's mark it. Oh, my favorite student. I thought I was your favorite student. No, it's Anne. What can I say? She gets perfect on everything. It's great. Position versus time graph. Position versus time graph. Everybody has the quiz. I got everybody that was away last day, right? Yeah? Okay. Here, forwards, constant speed. A. To the right, constant speed. Here, at rest, E. Standing still, not moving. Backward, constant speed. To the left, constant speed. B. At rest. And at rest back where he started from. So A, E, B, E? Yes? Okay, velocity versus time graph. Velocity versus time graph. Now I got to think about this a bit more. How is she moving in part 2? Part 2 is that chunk right there. That's forward, constant speed. I think that's also A, yeah? To the right, forward, constant speed. And part 4, that's this chunk right here. That's at rest. How is she moving in part 1? Forward or to the right, speeding up? How is she moving in part 3? To the right still, but slowing down. To the left would be below the x-axis. So one mark for each of those. Then number 7, I'll draw it and then I'll explain how I would give out the part marks. But for what it's worth, each one of these is going to be worth, count them, 2 marks. Okay? Let's do the position versus time graph first. A student walks at a constant velocity down the hall. I'd be looking for a line that was slanted upwards. Suddenly she stops. I'm looking for a horizontal chunk. I'm not too fussy how high or how long it is, but slanty line connected to a horizontal chunk. She runs backwards. How would I show backwards? Downhill. How would I show runs compared to walks? Okay, so I would be fussy here. This line should be downhill and steeper than your first line. And then she stops at her locker and she looks for her book. I would look for a horizontal line there. In fact, I notice I drew 1, 2, 3, 4 lines, 2 marks. You know what? Half mark for that line, half mark for that line, half mark for that line, and a half mark for that line if you want to know how I give out part marks. Now, the velocity versus time graph. She walks at a constant speed forwards. I would look for a horizontal line as your first line. Suddenly she stops. Horizontal line on the x-axis for your second line. She runs backwards. How would I show backwards on a velocity versus time graph? Below the x-axis. How would I show runs compared to walks? Further down. So I'm going to look for a horizontal line, and it has to be further down than your first line was up. And then she stops looking for the book. Hey, I drew 4 line segments there too. How about half mark, half mark, half mark, half mark? Can you give yourself a lovely little score out of 10, please? Now, of course, is the time to come lawyer with me if you need to. Not that the numbering means anything. Last lesson, we looked at velocity versus time graphs. I'm going to talk about question 5, the last question, because I said that was a nasty 5E. But were there any other questions before or besides that where you were getting, I don't know what to do here? Now is your chance to ask. You can also hit me up during a flex block, and a number of you have. That's great too. Any questions from the homework? So 5E, the answer was 12.5. And I always pause and I say, did anybody figure out a way to get the 12.5 without me telling you how to get the 12.5? Did anybody get 5E on their own? Because that was the nasty. A couple of you? Nice. You ready? One of the things I want to teach you, especially in Physics 12, is what I call stubborn cleverness. What I want to teach you, Zach, especially in Physics 12, is what do you do when you don't know what to do? Because most of you are high-achieving, nerdy students, and you usually know what you're doing. And most of you are probably post-secondary bound. And I figure one of the things I could teach you, and my Physics 12s have heard this speech, is I will always, in Physics 12, put one question on the test they've never seen before. And that's on purpose. Because I want to teach them what to do when they don't know what to do. It'll be a question that they know how to do, but they're going to have to combine this and this and this and this to get it. So, stubborn cleverness is a phrase that I use. I'm not going to quit. I'm going to go really, really systematic. Oh, let's pause the video for just a second here. First thing I always ask is, what are they asking me to find? What are they asking me to find in 5E? It's meant to be pretty obvious. If you can't get that part, we're in trouble. What are they asking me to find? You know what? I like writing stuff down. I'm going to write down displacement equals question mark. When I wrote that down, something jumped into my brain from the green sheet. The fact that on the green sheet, displacement is average velocity times time. I was grasping at straws. I said, I got to try something. Wait. I said, interval A, that's this chunk right here. I can tell you the time. How much time elapsed? I said, huh. So I said, huh. If I could somehow find the average velocity over that interval, I'm good to go. So I stared at this graph for a while. And I said, how can I find the average velocity on this interval? And I had a brainwave. Ready, Josh? Let's suppose you have $10 and I have $20. What do we average between us? I don't have how you say it. 15. How do you get 15 from 10 and 20? What did you do? In the middle, I'll take that. Or add them up and divide by 2, I think is really, okay. How could I find the average of two things? Add them up and divide by? How can I find the average of two things? Add them up and divide by? How can I find the average velocity? Here's the first velocity, 0. Here's the final velocity, 5. What did I average? 2.5. Yeah? I was grasping at straws here, but I said, wait a minute, that is what I averaged. My average velocity is 2.5. And if you go 2.5 times 5, you'll get 12.5 meters. Now, under hashtag cool nerd trivia, let's go back here for a second. I'll show you another way to do it. What kind of a graph is this? Velocity versus time. What's the slope of a velocity versus time graph? Tell us. This was the key idea. What's the slope of a velocity versus time graph? Tell us. It was the key idea. Acceleration. Ready, Parmjot? This is purely nerd trivia, but it's kind of cool. What's the area underneath a velocity versus time graph? Tell us. Turns out that area right there tells you the distance. If you calculate that area, it's 12.5. What shape is that yellow thing that I've colored in? Area of a triangle is base times height divided by 2. What's the base? 5. What's the height? 5. What's 5 times 5? Divided by 2? 12.5. Okay. So this is, if you're wondering, we haven't talked much about areas under graphs, but for example, if you wanted to figure out how far you'd gone in the first 15 seconds, it would be that whole area. How would I figure that out, Mr. Dewick? Well, to be frank, if I wanted to find the area for the first 15 seconds, I'd probably divide it up into a triangle, another triangle, little rectangle, and a rectangle, and I just add them all up. That's how far I've gone. I'm not going to ask you that on a test or anything like that, but it is kind of nerdily cool. Areas mean something too under graphs. We don't talk about that too much in Physics 11. We talk about it more in Physics 12. You talk about it hugely in calculus. Calculus was invented for two things, to find the slopes of curves and to find the area under curves. And it can, with a bit of work. Any other questions from the velocity time graph lesson, lesson 4? So if you have that done, could you hand it in? Little reminder, I am going to be emailing out an update to your parents and you tonight. So anything you hand in by the time after school rolls around, I'll type it all in. I'll stay after school. I'll type it all in. But since tomorrow is student-led conference day, I'm going to make sure you and your folks know if you're missing any assignments. Last lesson of the unit. I think I'm going to get partway through it today, and I'm going to finish it off when I see you guys next week. Relative velocity. Oh, I'm showing you graphs. Hey, here's a great one. This is called a graph of life satisfaction. So the red graph is for most people. Their maximum life satisfaction occurs in their 20s, and it goes downhill from here. But I would argue the blue graph for nerds, as you get older, life just keeps getting better and better and better and better, I think. I like that. Just saying. Relative velocity. Or, hey, what if you have two objects moving at the same time and you don't feel like graphing both of them because it becomes tedious? And that's your trigger. You know on your test, which isn't that far away, you know in your homework that it's a relative velocity question because there's two objects moving with different speeds. Relative velocity, two objects moving with different speeds. So, here's our first little thought experiment. You're driving down the freeway with your speedometer reading at 100 kilometers per hour. We'll go kilometers per hour because that's what speedometers show. And a white Escort hurtles by you at 140 kilometers per hour. Can you imagine that? You've all been on the freeway. A car has just gone past you. Suppose a tow truck was parked at rest beside the freeway. What would the tow truck see? What we're really asking is, we're talking about relative velocity. How does one object see another object traveling relative to it? And so I wrote down here the velocity of U relative to the tow truck. And then I said the velocity of the Escort. You know what? That's too much writing. Too much writing. You know what? Let's get clever. Draw a little line over here. Let's use a capital Y as our abbreviation for U. So rather than writing out the word U, capital Y. What would be a good letter to use for tow truck? I'm going to use a capital letter T for the truck. What would be a good letter to use for the Escort? Capital E for Escort. Okay. And then we're going to use that symbol for relative to. You don't even write that down, you'll figure it out. So the first question says U relative to the tow truck. If I was writing that, I would go V of U relative to the tow truck. All right. I'd like you to imagine the tow truck driver. You go zipping past. What does the tow truck driver see? How fast are you going relative to the tow truck driver? The tow truck driver is at rest. Don't overcomplicate it. How fast are you going relative to the tow truck driver in kilometers per hour? 100. What direction does the tow truck driver see you traveling? Well, if he sees you in the rear view mirror, he sees your headlights getting closer, forwards. Or if he sees you in front of him, he sees your taillights receding, still going forwards. So I'm going to argue that your velocity relative to the tow truck driver is positive 100 kilometers per hour. Doesn't seem profound yet. Wait till we get two objects moving. Patience. What does the tow truck driver see the Escort traveling at? What's the velocity of the Escort relative to the tow truck? Well, velocity of the Escort relative to the tow truck is, I guess, as a magnitude 140, because the tow truck's standing still at rest. And the tow truck would also see the Escort moving forwards. When he looked in his rearview mirror, he would see the headlights of the Escort getting closer, moving forwards. Or if the Escort was going past him, he would see the taillights receding, moving forwards. Okay with that? Positive 140 kilometers per hour. That's not that profound because only the cars are moving, the tow truck is not. Now let's look at what if both vehicles are moving. What would you see? Okay. What is the velocity of the Escort relative to you? Now we would write that velocity of the Escort relative to you. How fast do you see the Escort moving? If you're moving at 100 kilometers per hour and it's moving at 140 kilometers per hour, Raven, 40. Forward or backwards? Well, let's imagine if it's behind you and you look in your rearview mirror, you would see the headlights coming towards you forwards. And if it's in front of you, you would see the taillights receding. So I'm going to argue positive 40 kilometers per hour. We call that its relative velocity. Its relative velocity relative to you, positive 40. I wrote down here why. Are you okay with the explanation? We've been able to use our imagination. I'm not going to do a big English explanation. What about the tow truck? How would you see the tow truck traveling relative to you? Well, what would you see its speed at relative to you as a magnitude? So you ready? I'd like you to use your imagination. Let's suppose you're behind the tow truck, coming towards it. You would see the tow truck's taillights moving towards you. I know you're the one that's moving, but imagine you're standing still. It would look like the tow truck's taillights were coming towards you. How fast would they look like they were coming towards you at? 100. But you would see the taillights coming towards you as though it was traveling what direction? Backward. Backward. Or once you're past it and you look in your rearview mirror, you see the headlights moving further and further away from you as though Kennedy mathematically was backing up and you were standing still. We would say that the relative velocity of the tow truck relative to you would be negative 100 because relative to you, it's moving backwards. You're leaving it in the dust. Is that okay? You gotta kind of imagine each situation here. What would the Escort see? Okay. What would the velocity of you relative to the Escort be? So as the Escort is approaching you from behind, they would see your taillights getting bigger and bigger and bigger and bigger and bigger, as though you were backing up, mathematically. As the Escort went past you, they would see your headlights getting smaller and smaller and smaller and smaller, as though you were backing up. So relative to the Escort, your velocity is negative. How big? Raven. And what about the velocity of the tow truck relative to the Escort? Well, first of all, what's the speed difference between them? 140. That's going to be the magnitude. What about a velocity? Well, again, as far as the Escort is concerned, if it was standing still, it sees the tow truck receding backwards in the distance. And you kind of have to imagine that the Escort is standing still. I know it's not, but you can imagine the Earth is kind of rotating underneath its wheels and everything's going back in the distance. So the Escort would see the relative velocity of the tow truck as negative 140 kilometers per hour. I wrote down here, Dorian, Mr. Duke, is there a short way to write this? Yep. Actually, I did it with you already. The first time I taught this, we wrote everything out in English, velocity relative to the, and I said, forget that. I'll show them the abbreviations to begin with because I tend to abbreviate. So here's the short way to write this. Pick letters that make sense and the symbol for relative to an arrow pointing. Velocity of the tow truck relative to you. Velocity of you relative to the tow truck. So, you don't perceive the Escort to be moving away at 140 kilometers per hour because you're moving already. You see it going past you at a relative speed of 40 kilometers per hour. The Escort sees you backing up at 40 kilometers per hour, but the relative speed between you is 40 kilometers per hour. The relative velocity or relative speed of any moving object depends on your point of view, or the fancy word, Evan, your frame of reference. Okay? You might have experienced this if you've ever walked on a moving walkway at an airport and there are pedestrians walking on the level ground that's not moving. You're walking slowly on the walkway if you look down at your feet, but if you look beside you, it looks like you're jogging or almost running because you see the walls moving past you much faster than you feel like you're walking. That's a lovely relative velocity situation. Two objects moving, the walkway and you. What's the velocity of the train passenger relative to the observer on the ground in each case? So let's suppose this train is moving to the right at 15 meters per second, and this person is walking to the right at 1.2 meters per second. How fast would this guy on the ground see this person walking? Or as an abbreviation, what would the relative speed be? My abbreviation for relative speed is REL. What do you think? 1.2 meters per second to the right and 15 meters per second to the right. What would this guy on the ground see the person walking at? Yeah, 16.2 meters per second. Because they're both in the same direction. What about this second situation where the train is moving to the right at 15 meters per second and the guy is walking to the left at 1.2 meters per second? What would the relative speed be? Yeah, 13.8. Don't write this down, just as a little thought experiment. What if this guy was running backwards at 15 meters per second? Pardon me? Put your pencils down, look up. Let's add some life and death struggle to our physics. A zebra is running away at 50 kilometers per hour from a cheetah that is going at 90 kilometers per hour. First of all, let's talk about their frame of reference. What velocity does the zebra see the cheetah having, and vice versa? What would be a good letter to use for zebra? B, Mr. Dewick? No. How about Z? Yes? What would be a good letter to use for cheetah? How about H, Mr. Dewick? No, how about C? Let's use the first letter of each word. That would work much better. Yes? Okay. So, the velocity of the cheetah relative to the zebra is what? First of all, what's the magnitude of the velocity? One's going 50, one's going 90. They're going in the same direction. What's the magnitude? Darryl. Okay. Good. 40 kilometers per hour. Now I want to decide, is it positive or negative? So I imagine I'm the zebra. If I had a rear view mirror, I would see the face, the headlights, the front end of the cheetah getting closer and closer and closer and closer and closer. I think relative to the zebra, the cheetah is moving forward. What about the velocity of the zebra relative, the velocity of the zebra, Mr. Dewick, relative to the cheetah? I think the magnitude is still, Zach, going to be 40. still going to be 40. Except, what does the cheetah see? Well, the cheetah sees the hindquarters of the zebra getting closer and closer and closer and closer, and dinner's ready. So as far as the cheetah is concerned, if we imagine the cheetah is standing still, its brain sees the zebra slowly backing towards it. How would I show backing towards it? Negative. Negative. Now, I'm not going to be that fussy on positive and negative. In fact, most of the time, we're not going to use relative velocity. We're going to use relative speed. Don't care about the direction. And in fact, in this next question, part C, I like part C, I like part C, I like part C is the next question. We're going to use relative speed. It says this, if the zebra starts out 90 meters ahead, how long will it take until the cheetah catches up? What's this question asking me to find? Yeah, I think time. Someone said distance. How long can mean distance, but I think they gave me a distance there. So I think time. So let's all of us, until we get really good, let's write down T equals question mark. What's that 90? D equals 90 meters. We're going to use this equation here from your green sheet. We're going to use distance equals speed times time. D equals VT, which is on your green sheet. But here's the nice thing. If there's more than one object, I can use relative speed, VREL, times time. I want to get the time by itself. How would I get the T by itself? What's the V doing to the T? Adding, subtracting, multiplying, or dividing? What's the V doing to the T? Adding, subtracting, multiplying, or dividing? Sorry? Multiplying. So how will I move it over? So here's an equation for time. This one is not on your green sheet. Time is D over V. In fact, it also works for relative speed. Now, what is the relative speed? What did we say in part A and part B as a magnitude? What's the relative speed between these two animals? 40 what units, please? Kilometers is not a speed. No. What did I... Go look, please. I put units next to my answers. Up there. 40 what? Per hour. That's a speed. And I do a bit of a problem here, Kyle. Here's my problem. Kyle, can you read me this? 90 what? Can you read me this? Kilometer. We need to do. We can't do math with kilometers per hour and meters. We could convert this to kilometers. You know what? Let's convert this to meters per second because we have a shortcut on our green sheet. I remember that shortcut had something to do with a 3.6. Do I times or do I divide? Someone look it up. Or if someone has it memorized, I don't care which. Times or divide? Someone check. Is it divide? Yes? Is it? Okay. So if I go 40 divided by 3.6, by the way, I will probably, especially if it's a car question, give you the speeds in kilometers per hour and want the answer in meters and seconds, so you'll have to do a conversion. It's going to be 40 divided by 3.6. Okay, 11.1111. I'm going to write 11.1 meters per second. But I'll store this number on my answer on my calculator. So, how can I find how long this takes? The distance is 90. What's the relative speed in meters per second? Now, I'm going to go 90 divided by, and I'm going to use my answer button rather than go 11.1 because I really like to divide by 11.111111. And I get what? 8.1. And units would be seconds. So let's put this in perspective. Let's suppose that safety is 7 seconds away for the zebra. Or let's suppose the cheetah will tire after 7 seconds. Zebra survives. Let's suppose that safety is 8.5 seconds away. Or the cheetah can run for 8.5 seconds. Dinner is served. And I mean, I'm kind of being a little bit facetious and sarcastic, but actually this balance is really what goes on in nature all the time. Most of the nature documentaries, if you watch them, most animals, it's always this close to surviving and starving, surviving and starving. In fact, the zebras can do this math on their own pretty accurately. If you watch nature films, you'll often see a herd of zebras and there's some cheetahs or some lions nearby, and the zebras are, whatever. What they're really doing is they're calculating the distance between them and the prey. They know how fast a lion travels. They're figuring out how long it would take, and they know how long that animal can run before it tires. And if you watch, the cheetah or the lion will get a bit closer, the zebras or whatever, closer, zebras or whatever, and then all of a sudden there comes a point when the zebras have done the math, and now you'll have a stampede. But you don't want to stampede unnecessarily because it's a massive waste of energy. You only want to run if you need to run, because you're always that close to starving and surviving. Nature's not nice, right? It's survival of the fittest. Put your pencils down, look up. What was the plane's velocity relative to the ground? 0 meters per second. What was the plane's velocity or speed relative to the wind? Whatever it needed for takeoff velocity. Right? Example 3. Says this. State the relative speed in each case. Okay, I'll zoom in so you know which one we're talking about. So here's the first one. Let's imagine they are, two cars. One's traveling 40, the other's traveling 40. What's their relative speed? That one's meant to be fairly obvious, I hope. What's their speed relative to each other if they're both going 40? 0. If a car pulls up next to you and matches the same speed as you, you can look, their faces aren't blurred, they're not zipping by. Relative to you, they're at rest. They're both 0. What about here? If one's going 40 and the other one's going 20 and they're in the same direction, what's their relative speed? You're right. 20. And the one in front would see the one in back going forwards. The one in back would see the one in front going backwards. I don't care about velocity. I just want the speed, so I'm not worried about positive or negative. Ooh. What if they're heading towards each other? What's the relative speed? This is why head-on collisions do so much more damage than getting rear-ended. Right? Way more. So let's do a question. I like example 2. I like example 2. I like example 2. Example 2 is a nice question. It says this. How long does it take these trains to completely pass each other? What's this question asking me to find when it says how long? Distance or time? I think this one's time. Okay? So down here, let's write down t equals question mark. Now, here's my argument. Follow closely. I'm going to argue that the definition of the back train passing the front train is, Krisha, the back end right here has to pass the front end of the front train. That's passing. What distance does that back end have to travel relative to the front end of the train? Yeah. Now, I know they're both moving forward. I don't care. I'm going to ignore the fact that they're moving forwards. I'm going to pretend that that front train is standing still and the back train is moving relative to the front train. And so I'm going to argue, Sarah, that the distance we need to travel is that. I'd like to have a speed, but here's the key. Is there more than one object moving in this question? Are they moving at different speeds? This is a job for relative speed. What's the relative speed between these two objects? Check your math. 8. 8, yes? The difference in speed between them is 8. By the way, what if they're heading towards each other? Then I would add the two numbers. Okay? But in the same direction, subtract. I'm looking for an equation. There's a d, a v, and a t in it. Hey, there is one. This one. And it even works for relative speed. I'd like to get the t by itself. What's the v doing to the t? Adding, subtracting, multiplying, or dividing? Multiplying. How will I move it over? Divide. You might end up memorizing this equation. I didn't put it on your formula sheet on purpose because it's really easy to derive, or it will be as you get good. It's the distance divided by the speed. In this case, we're going to use the relative speed because we're using a relative distance. It's going to be 250 divided by 8, which is what? I get 31.25. By the way, just to review, 13.0, how many sig figs? How many sig figs? It's 3, right? The point 0, 3. 5.00, how many sig figs? 3. 100 point, how many sig figs? Spot the trend. 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. Technically, how many sig figs should I go to in my answer then? 3. So I'm going to go 31.3. If you wrote 31.25, I'd give you full marks, but I figured it was a nice chance to review some sig figs, which apparently some of you needed the review on. 31.3 seconds. 31.3 seconds. Turn the page. Airport walkways are terrific examples of relative velocity. All those walkways are designed to do is reduce time, right? We want to get you to your flight faster because the more people we can pack through the airport, the more money the airport's going to make. It's an investment. The more of those walkways that we build, the more people we can get through the airport, the more money we can make. I have a take-home quiz for you. So take a look at the take-home quiz, number 3. It's called More Motion Graphs. On the front page, I'm not going to be too fussy. I want you to just sketch the shape. So we have position time and velocity time graphs. A fast buggy starts ahead of the origin and moves forward at constant speed. What would that look like as a position and a velocity versus time graph? Turn the page over. On the back page, because I've given you grid paper with numbers, which means you can find the slopes accurately, I will be fussy on your heights and your steepnesses and your slopes for whatever graphs that you draw. So on number 5 and number 6 and number 7, I will be fussier. Okay? I won't just say get the shape right. You're going to have to get the height right too. Then number 8, number 9, and number 10 says, for the 3 graphs above, that's 5, 6, and 7, rank them from smallest distance traveled to largest distance traveled, rank them from most negative displacement to most positive displacement, rank them from most negative average velocity to most positive average velocity. This quiz is out of 14. This is due Tuesday, but I'm trying to give you 8 minutes. If you want to get it done in class, I think you can.